Hey, have you ever wondered how scientists can forecast things like the weather or where a ball will end up if you throw it? They use cause and effect. When something happens, like throwing a ball, that's the cause, and what happens next, the ball flying, is the effect. If we could measure everything perfectly, like the ball's speed and direction, could we predict where it will land or what happened before it was thrown? Determinism is the idea that if we know enough about something, we can predict the future or the past. We are going to explore some really fun ideas about the world around us and how we can understand it better. We'll talk about cause, effect, and how we can sometimes predict what's going to happen next. Let's start with something we already know: cause and effect. Imagine you kick a soccer ball. The cause is you kicking the ball, and the effect is the ball rolling across the field. Now, what if we could measure how hard you kick the ball and how far it rolls? We could figure out a lot about what happened, right? The stronger the kick, cause, the farther the ball goes, effect. So, both the cause and effect can be measured. Now, here's something even more amazing. Guess what? You can also figure out the past. If you see the ball stopped at a certain spot, you can think back and figure out how hard it was kicked. This brings us to something called determinism.
When we kick a ball, the force we apply directly affects how far it travels. Think about it. If I give the ball a gentle tap, it barely rolls away. This is because the force is too weak to overcome friction and inertia. Now, if I really put my strength into that kick, the ball zips off, covering much greater distance. This happens because the harder kick generates more force, propelling the ball forward with greater speed. In physics, we call this relationship cause and effect. The cause is the strength of my kick, and the effect is how far the ball travels. So, next time you kick a ball, remember, the harder you kick, the farther it goes. Understanding this principle not only helps in sports, but also in grasping the basics of motion and energy in our everyday lives.
But sometimes, things aren't as clear. Let's take a coin toss as an example. When you flip a coin, can you always be sure it will land on heads? No, it could land on heads or tails, and we can't be certain about the result. That's what we call probabilistic. It's like playing a guessing game. Things could go different ways, and we have to wait and see. Now, let's imagine you wanted to figure out how often the coin lands on heads. If you flip it 10 times, maybe you get heads 6 times and tails 4 times. Then, you flip it 100 times, and it gets closer to 50 heads and 50 tails. That's where we use statistics to understand patterns. Statistics help us see what usually happens, even though we can't be certain every time.
To the naked eye, our world appears orderly and stable. A glass of water resting on the table looks still, but if you zoom in on the atoms and molecules that compose the water, you would see that actually they are moving. The microscopic world of fluids is animated by countless particle collisions, moving atoms and molecules on wandering trajectories. This random movement of particles is called Brownian motion. In 1827, botanist Robert Brown first discovered this phenomenon after observing that pollen grains jitter when immersed in water. For several decades, it was unclear why small particles would dance when suspended in a fluid. Some scientists thought that there was some sort of life force driving this movement, since pollen comes from plants. But it was soon discovered that non-living materials, like dust and iron filings, exhibit the same jiggly behavior. In 1905, the mystery began to unravel. Albert Einstein modeled the motion of Brown's pollen particles as a result of being bombarded by individual water molecules. In Einstein's model, the water molecules bombard a pollen grain from different directions, some directions more than others, resulting in its seemingly random motion. While ancient Greeks and Romans had theorized about atoms and molecules, Einstein's work validated the centuries-old idea that units of matter too small for our eyes to see actually do exist. By understanding Brownian motion, Einstein was also able to accurately determine the size of atoms and molecules. Brownian motion can explain a wide range of processes, such as the movement of bacteria and proteins, the diffusion of calcium through our bones, the spread of pollutants through air and water, and even the movement of viral particles through the air. Scientists also use mathematical models of Brownian motion to describe fluctuating social phenomena, such as stock prices, the transmission of disease throughout a community, and the spread of rumors in social networks. This is because human behaviors, like Brownian motion, involve randomness. Many of the decisions we make about things like buying stock or socializing are influenced by a combination of innumerable complex factors, such as the weather, what we ate for breakfast, or whether our neighbor said hello to us on the street. Brownian motion also plays a central role in recent and emerging technologies, particularly those that depend on the process of diffusion, the movement of particles from an area of high concentration to an area of low concentration. Brownian motion is integral to understanding diffusion since the latter involves small particles suspended in a fluid. Exciting applications of diffusion include generating energy from salinity differences, designing dialysis machines for removing waste products from blood, creating batteries for storing energy, and desalinating water to make it potable. Despite operating on a minuscule scale, Brownian motion is fundamental to understanding how our world functions, and it will continue to play an important role in the technologies that will shape our future.
Finally, have any of you heard about Brownian motion? It sounds fancy, but it's really about tiny particles, so small you can't even see them, moving around in random directions. It's like watching dust float in the air when sunlight shines into a dark room. The dust moves in all directions, and it's very hard to predict where it will go next. The ball you kicked in one of the previous examples is something big that you can see, touch, and interact with. These kind of objects are called macro objects. Look around you and see if you can name some macro objects. Look around the room. What do you see? Maybe your desk, your books, or your friends. These are big things, and we call them macroscopic. That means things you can see with your eyes. Now, let's think about tiny things. Imagine the smallest thing you can think of. Well, as things get smaller and smaller, At some point, we stop being able to see them. For example, you can see an ant, but if you keep shrinking smaller than an ant, eventually you'll get to things like dust and even tinier particles, like atoms. That's where the macro world ends and the micro world begins. Now, do the big things and tiny things follow the same rules? Imagine throwing a ball. It flies through the air and lands on the ground. We can predict how it will move because of the laws of physics. But what if we are looking at tiny particles, like atoms? Do they behave the same way as a ball? Well, not exactly. But why? Atoms and particles don't always behave like we expect. Let's talk about atoms for a minute. You might have heard that everything is made of atoms. But a long time ago, people thought atoms were like tiny, solid balls. Then, scientists discovered that atoms are actually made of even tinier parts, like a little solar system, with a nucleus in the middle and electrons whizzing around. Our understanding of the atom has changed because we've learned more and more about the world through experiments. Here's a cool experiment you can even try to imagine. What happens when you shine light through a small opening, like a slit? The light spreads out. But if you shine it through two slits, something really weird happens. The light doesn't just make two spots on the other side. Instead, it makes a pattern of bright and dark spots. This is called the double slit experiment. It shows us that light can behave both like a wave and a particle. It's like light is playing a game we didn't even know about. Finally, let's talk about something you've probably noticed. When things get really hot, they glow. Like when you see a metal rod in a fire, it turns red, then orange, and if it gets really hot, even white. This is called the radiation spectrum. When things heat up, they give off light, and the hotter they get, the brighter they glow. Have you ever seen a glowing stove? It's giving off light because it's so hot. Alright, let's talk about atom. Think of an atom as a tiny building block. It's super small. Inside an atom, there are three main parts. First, we have proton. They have a positive charge. Next, there are neutron. They don't have any charge. Both proton and neutron sit together in the center, called the nucleus. Lastly, we have electron. They have a negative charge and move around the nucleus. That's the basic idea of an atom.